From our paired t-test, we learned that after 1 week, the banana peels are thinner. But we did have to cut the bananas to measure that. Perhaps cutting them allowed water to evaporate from the peels, making them lose weight and seem to be thinner. How can we test if the peels get thinner over time without compromising the results? You sample 30 bananas in groups. You get 6 green bananas, 6 yellowing bananas. They're starting to ripen but not quite ripe yet. 6 fully ripe yellow bananas, 6 browning bananas. They're starting to get some spots on them. And 6 really brown, mushy bananas. Now, you want to compare the peel proportions for each group to see if the proportions change. This is called a one-way ANOVA. T-tests compare a variable with 2 categories, like a hypothetical mean with an actual mean, or vendor A with vendor B, or week 1 and week 2. ANOVAs are used when you're comparing a variable with 3 or more categories. So for an ANOVA, your data will look something like this. You run your ANOVA test, and it tells you that peel proportions are not different between color groups. Peel proportions are the same whether the bananas are solid green or black and mushy. This implies that cutting the bananas may have affected the peel proportions, since when we cut the bananas there was a difference, and when we didn't cut the bananas there wasn't a difference. In statistics, this is called a confounding variable, something that wasn't part of your analysis, yet it has an effect on your results. So the reason this type of test is called a one-way ANOVA is because there's just one variable here we're analyzing, color. Suppose we suspected there are seasonal variations in banana peel proportions. We could add another variable for season. Then we'd sample bananas and record the color and the season. This would be a two-way ANOVA. We'd analyze both variables together to see if there are any interactions, meaning the value of one variable depends on the value of another. For example, green bananas are thicker in the winter than in the summer, but all other colors of bananas are unchanged. To collect data for a two-way ANOVA, you'd follow this table. Every level of color gets sampled for every level of season. This type of ANOVA is called balanced factorial design. There are other designs that get analyzed differently, but that goes way beyond the scope of this tutorial. So here, we sampled 6 bananas for each combination, which is just an arbitrary number. You could sample more or less, but you generally want to have more than 3. Remember, more is better, at least as far as a statistical model is concerned. It's not necessarily better for your budget, so you have to strike a balance. But please note, you needed to test 30 bananas for the one-way ANOVA. With the two-way ANOVA, you now have to test 120 bananas. This is why you have to be strategic in your experimental design. Every factor you add exponentially increases the number of samples you need to collect, and each sample costs time and money. But aside from the time spent on each sample, you've also greatly increased the timeline for the entire experiment. With the one-way ANOVA, you could have found enough bananas of different coloration in a day or 2, or at most 2 weeks. But now that you're investigating season, you have to collect and test samples for an entire year before you can get your results. Can your new marketing campaign wait that long? If it can, you could actually compute your new average peel proportion based on the samples you took for your two-way ANOVA. You'd have an average of 120 bananas rather than 30, and it would cover a wider spectrum of your variation. So that would give you a more accurate number to go off of. But let's say you can't wait that long. You could just use your reference number and perform quality control checks at regular intervals to make sure you're still within range. If the peel proportions start changing, you update your catch register algorithm. Even if you went the long route and conducted the two-way ANOVA investigating season, you'd still want to do the regular monitoring to make sure your algorithm is functioning properly. There are different methods of monitoring, and an explanation of them would be an entirely separate tutorial. However, you could use what you've learned about t-tests in this tutorial to come up with a quality check method. Think about comparing a sample against a reference value, or one sample against another.